Hello, hello.
In this lesson, we're going to take a look at two different enrichment technologies which are collectively known as the aerodynamic enrichment methods. Now, the first one we're going to look at was developed in Germany by some guy named Becker, and it's known unsurprisingly as the Becker method. Now, the Becker method uses kind of a similar principle to what we saw with gaseous centrifuges. That is, it takes our feed, our UF6, and it puts it on a curved path. And what happens is our centrifugal acceleration is going to take and push the heavier stuff out to the outside radius of a curved path while keeping some of the more enriched U-235 stream to the inside of the path. Again, very similar to what happens with gaseous centrifuges. Now, if you look at the little diagram here on the screen, what you'll see is a couple of things. So we have a channel over here on the left-hand side that our feed gas is coming in on. It goes around this little obstacle into a curved path. This is what provides that radial acceleration, which is going to try to separate out the two different parts of the UF6. And then it has this little tiny finger that sits here. And what this does is it basically provides a forcing function to take the heavier stuff that's on the outside of the curve into one path and the lighter stuff on the inside of the curve to a different path. Now, one of the things to note is that with the aerodynamic methods, both this one and the Helicon, which we'll talk about in a second, both of them use diluted UF6. That is, molecular hydrogen gas is used as, we'll call it, a carrier gas. And it's mostly that hydrogen gas. In fact, it's about, for the Becker nozzle, it's about 96% hydrogen and only 4% UF6. So why do we do this? Well, the reason is that UF6 itself, because it's uranium, is quite heavy. And there was no real way to get adequate separation between the lighter 235 and the heavier 238 molecules with just the UF6. They couldn't get it to move through this fast enough. You can notice with the little scale here, which is 1 millimeter, that this thing, these nozzles, as they're called, were created on a very, very small scale, tens to hundreds of microns. And at this scale, it just wasn't happening. They just couldn't get that separation to occur. But by taking and cutting it or making it mostly hydrogen gas, they could get it moving fast enough to provide that radial acceleration, which gives us our separation potential. So when I say here on the slide, it provides a semi-hysteresis effect, well, what that means is the hydrogen basically drags the UF6 molecules along with it at a much higher rate than would normally be achievable. Now, there's no moving parts here. This nozzle is basically a piece of metal that was etched to very precise specifications. Actually, it's kind of a stack of very thin metal pieces that were etched to these specifications, and then they kind of welded them all together to get something that was relatively thick that could actually be used. So no moving parts whatsoever. One thing that you should probably be aware of is this little finger here that actually performs the separation between the light and the heavy components of our gas. That is the most critical part to the entire assembly. If you get that wrong, then your separation really doesn't happen. Now, this is just one nozzle by itself. Now, one nozzle by itself isn't really going to provide either the throughput that you would need if you were trying to have an enrichment program that had any kind of amount of product coming out. So what they would end up doing is putting a bunch of these together, kind of like a little mini stage. And what they would do is they would put maybe 10 of these things together to increase the amount of separation for that particular stage. The fabrication techniques at the time, these were very well known. They're still very well known, and actually we have increased the amount of precision to which we could fabricate something like this in modern times, but it's still not used. As far as I'm aware, there's an original article that describes the method and several things that they did, including putting together these semi-stages, these 10 nozzle setups, and then put 10 of those, or many of those, into 10 large type stages in order to get good separation. So this is basically kind of how it works if they put a bunch of these nozzles together. And that's seen right here in this, this spoked wheel diagram, where we can see right here we have the setup we saw on the earlier page, or on the earlier slide, where we've got our gas coming in, we have our radial acceleration, and then we have our little finger right here that separates out, actually the finger's right here, separates out the gas into the lighter fraction, and then the heavier fraction goes down. So that would be occurring right here. So our lighter fraction would be coming out of this whole system, while the heavier stuff would go on to the next step and undergo the exact same thing. So in this way, you're getting a percentage of the total mass stream is being siphoned off at each one of these little individual nozzles. So a couple of things. One is that this is not a really efficient method. The amount of pumping the equipment that you need in order to obtain the velocities to get that separation. So a lot of power usage, so about 3,200 SWUs per unit product out. So not super efficient. Unlike the centrifuge, which once you get it up and spinning because of the frictionless bearings, it's not so bad, and it doesn't have to be pressurized. This unfortunately does, so it puts it in, as far as efficiency per unit product, somewhere around gaseous diffusion, actually. So the efficiency is determined by two things, the so-called cut and the aperture angle, which is the design of that little finger right there. Now, what's cut? Cut is simply how much percentage of the gas are we siphoning off at each one of these product outputs. So the cut for, I think for this particular one was, I want to say it was 25%. So 25% of the gas entering would leave through the light fraction. And then you would get more going on to the next stage. But again, you're constantly having gas moving through here. So for each one of these, you would see a reduction in the amount of product that you were pulling out. So for each individual nozzle, they had a proposed alpha of about 1.015. Now, this is better than gaseous diffusion, but nowhere near as good as a gaseous centrifuge. And this was per tube, so per this, I don't know how many stages are here, 10. Per 10 nozzle tube, they were getting about 1.015 again. Now, when they put it all together in a cascade, so what we see right here, what they ended up seeing was an increase in the alpha that was seen throughout the system to about 1.1, which is much better than gaseous diffusion, but again, not quite to the level of the gaseous centrifuges. But this method, again, from just the original paper and the work that they did that supported this research, this is the only thing I can find where this was ever even built. It was never used on large scale. No pilot plant other than the experimental setup you see here was ever constructed. So this is one of the aerodynamic methods. The second one is something called the helicon vortex, which was developed by South Africa. And if you'll recall, South Africa being the only nuclear weapon state to have voluntarily disarmed itself and removed all of its nuclear weapons under the auspices of international inspection. Now, South Africa was the only one that developed this. They were the only one that ever used it. And the way that it worked was very similar to a gaseous centrifuge. The difference being, instead of rotating a cylinder to get that radial acceleration to provide the separation that you need, what they did is they took kind of a cone-shaped container, and instead of spinning the container, they injected the gas at high velocities. Again, the gas is a mixture of both hydrogen gas and our UF6. And as it moved downwards, in this particular example, it was injected here, and as it moves down the cone gets smaller and smaller, and very similar to how figure skaters increase their rotational velocity by pulling their arms in towards their chest. The gas, as it moved into a tighter and tighter radius, would accelerate more and more, again providing more separation potential. Now there are two diagrams here. One shows that we're injecting not really at the very top, so we're injecting somewhere down the side of our conical container, and it shows us that as we get smaller and smaller, the lighter gas is going to stay in the middle, the heavier gas is going to go to the outside, so that we're basically going to take our product out of the middle, very much like we do with a centrifuge, and our waste stream is going to come from the outside, again, like a centrifuge. However, it's not very clear in public literature which of these two graphics I show here on the screen is actually how they built it. So the one that makes more sense to me is the one here on the bottom, showing injecting at the top of the cone and then taking both the heavy and the light fractions out of the bottom of the cone. Whereas this one, it has the product coming out the bottom and the waste coming out of the top. I don't know which of these is more accurate, but I've included them both just for completeness sake. Now the alpha, again per unit, is slightly higher than it was with the Becker nozzle. So instead of that 1.014, we're now up to about 1.03. There's also a lowering of the amount of mass or gas that we're taking out at any particular stage from 25% all the way down to 5%. So we're siphoning off very little per individual unit of these cones. So because of this, you can have many more streams going from stage to, or from unit to unit to unit, because you're only taking out a little bit, so you're not losing so much mass per each step. Now there was something else that was very interesting, and it worked specifically for the Helicon vortex, which was something called an axial compressor. Now an axial compressor can handle different streams of feed, like gas in this particular case, without mixing them. So you would think if you were sending several different streams of gas into a compressor, they'd all just get mixed up and you'd get a, some sort of average of whatever your gases were coming out the end. But with an axial compressor, this doesn't happen, or it happens to a very, very small amount to be almost negligible. So because an axial compressor can handle up to 19 individual streams with no mixing, a single unit of the Helicon vortex is considered to be 19 of these things. So we have a highly reduced amount of equipment that's going to be required in order to provide the same results on our output. Still, unfortunately, has the same power requirements as the Becker nozzle setup, because the axial pumps, while you need fewer of them, apparently they require a lot more power to run. And I guess that kind of makes sense, although I don't know enough about axial compressors versus normal compressors to make a educated judgment on this. Now, historically, again, South Africa are the only ones that used it. But as they dismantled the program, this has never, again, been used for uranium enrichment afterwards. Now, there's no information that's readily available. Obviously, you don't want to encourage proliferation, so any specific uranium enrichment designs are going to be held at some kind of classification level. But there is a company named Clydon, and Clydon kind of inherited, or they were the governmental institution that developed the Helicon vortex. They have been since commercialized, and they have shown that they can use this particular method for enriching things other than uranium hexafluoride. In fact, they built a pilot plant in 2008, but as far as I can tell, the only gas they've run through it is silane, which is a far cry from, the hydrogen UF6 mixture that would have been running through this during their weapons program. So it's actually quite a good method. Again, completely indigenously developed, operates on the same principles as the Becker nozzle and even the gaseous centrifuge, but has been basically considered obsolete with the development of gaseous centrifuges. So in the next lesson, we're going to look at the last two of the enrichment technologies that are of concern to us. And these are both laser-driven methods, one at the atomic level and one at the molecular level.